So far you've learned about functions and data, much the essence of programming. In fact, you've mastered the fundamentals of the Python language. So it's time to move on to a new language, Scheme. And by learning Scheme, we'll see that many of the ideas learned about one programming language easily transfer to another. And Scheme is an older language that was very influential in the creation of Python. So, we understand it for its history, its beauty, and also to see which ideas transfer from one language to another naturally, and we'll find that that's many of them. Scheme is a dialect of a language called Lisp, and Lisp is one of the two oldest programming languages that's still used today. And it's certainly the oldest one that's rapidly growing, because more and more people keep getting excited about using Lisp for new applications. What are people saying about Lisp? Alan Kay, the inventor of object-oriented programming, said that it's the greatest single programming language ever designed. My favorite sci-fi author said that it's the only computer language that is beautiful. And Brian Harvey once told me it's God's programming language. Even XKCD seems to love it. Lisp is over half a century old and it still has perfect timeless air about it. I wonder if the cycles will continue forever, a few coders from each new generation rediscovering the Lisp arts. These are your father's parentheses. Elegant weapons for a more civilized age. So, hopefully that gets you excited about learning a new programming language. The beauty of Lisp is its simplicity. The entire language can be learned in a day, and yet it can be used in order to build programs as complex as the ones we've seen throughout this course, or much more complex than that. Here are the fundamentals. Scheme programs consist of expressions, which can be primitive, such as 2 or 3.3, or true or plus is a primitive expression, or quotient, which does division, etc. And there are combinations. So a combination looks like an open parenthesis, and then some other expressions, and then a closed parenthesis. And in this way, we can express the quotient of 10 and 2, which is 10 divided by 2 is 5. Or we can express through combination that not true is false, etc. So numbers are self-evaluating, but symbols are bound to values. Call expressions look like combinations, and they start with an operator, followed by 0 or more operands, all in parentheses. So this is a little different than the syntax of Python. Normally we'd put the operator outside, but here we're putting it inside. So let's look at some examples. If at the scheme prompt I type open parenthesis, quotient 10, 5, 10, 2, close parenthesis, then I get 5. Quotient names the built-in integer division procedure. In Python we called things functions, in Scheme they're called procedures, but they're fundamentally the same thing. You can nest call expressions. I could say, what's the quotient of the result of adding together 8 and 7? Well, that's 15. Divided by 5 is 3. And if I want to, I can spread these call expressions across multiple lines in any way that I see fit. Here's a typical way to use indentation just to make the expression clearer. So this says I'm going to add two things, the result of this sub-expression and the result of this sub-expression. And that's why they're indented to the same level. Now the scheme interpreter doesn't care about indentation at all. These are here in order to make the program as readable as possible for people. So combinations can span multiple lines. Spacing doesn't matter. Going to new lines doesn't matter. All that matters is that you close the parentheses that you open. The way to read this is to say that we're adding together two things. The first is a product of two things. The first of that is 3. And then we need to add together what you get when you multiply 2 and 4 is 8, and you add 3 and 5, that's 8 again. So summing that together is 16 times 3 is 48. Okay, what about down here? Well, I subtract 7 from 10 to get 3, and I add that to 6. So I've got 9. 9 plus 48 is 57. So this whole expression would evaluate to 57. Let's do some more demonstrations. Here's a scheme prompt. I can evaluate 2. I can evaluate the sum of 1, 2, 3, and 4 is 10. What happens if I add together nothing at all, do you think? 0. I can multiply 1, 2, 3, and 4 to get 24, or I could multiply together nothing at all. 1. Okay, so I can multiply together 2 and 2 and 2 and 2 and 3 and 3 and 3. Oops. To get 864. And I can nest this, so if I then want to, let's say, subtract 1, I would do it by surrounding the whole thing in parentheses, placing a new operator at the front. And I can not only subtract, but I can also divide, add, or multiply again, anything I want to do. And the result will be computed using the normal call expression procedure, where first I evaluate the operator and operands, and then I apply the procedure to the arguments. So it's the same story as evaluating Python, but this time we put the parentheses in slightly different places. In addition to these arithmetic procedures that are built in, such as plus, there are also various other procedures built in. I can ask whether something's a number. 3 is a number, plus is not a number. I can ask whether some number is 0. 2 is not 0, which is why we get false. But 0 is 0, which is why we get true. So if I actually subtracted 2 from 2, I would end up with 0, which is true. And we can also evaluate whether something is an integer. 2.2 is not, but 2 is. Now these question marks are just part of the name. The name is integer question mark. And the reason the question mark is there is that it's supposed to help you figure out what the procedure does. So just like in any programming language, we'd like to use names that help remind us of what things are going to do. And this integer question mark name is a good reminder that this is something that returns false or true based on what its arguments are.